Hello and welcome to today's lecture. In the last lecture, we had introduced two important concepts of analysis of variance and experimental design. Okay. So, let us briefly do a recap of these ideas. So, for an experimental design, there are various components of an experiment. Okay. The subject on whom you do the experiment. Okay. So, this is also referred as experimental unit. The factor which you are changing, so it is a variable. Okay. The levels, okay. Levels refer to settings of the factor. Okay. You can have another thing called treatments. If there are more than one factor, then you might have more than one treatment, okay, and your final response, okay, which is what you measure. Okay. So, in experimental design, there are various ways of doing it. So, imagine you have k populations or k subpopulations, okay, k subpopulations. Okay. For a randomized design, okay, you choose random samples. Okay, so let me write it in the next page. For a randomized design or randomized experimental design, okay. So, random samples are selected independently from each of k populations. Okay. So, this is called a randomized design. So, in this, of course, your factor is the population itself. Your number of levels are 4 are k, as there are k subpopulations. Okay. So, the question with these designs, with these experiments you want to address is, are the k population means same or not? Or not. Okay. So, essentially you want to test the hypothesis that if you have k populations, you want to test mu1 equal to mu2 equal to mu k. Okay. So, as we discussed in last class, you can do this using the t test. Okay. So, you can do this using the t test, but in that case you will have various hypotheses you have to test. So, for example, you have to test the hypothesis mu1 equal to mu2, hypothesis mu2 equal to mu3, and so on and so forth, okay, which is tedious and it also introduces error. Okay. So, this introduces error. So, ANOVA, okay, short for analysis of variance, allows you to answer this question, that are the k subpopulations, are the k population means same or not, in a single test. Okay. So, what do you exactly do in ANOVA, okay, and what are the assumptions? So, the primary assumption of this approach is that the observations within each population are normally distributed with variance sigma square. Okay. So, essentially the variance for each population is the same. Okay. So, in ANOVA, okay, let us say Xij corresponds to jth measurement in ith sample. Okay. In short, you have, let us say, k samples or k populations, k samples corresponding to k populations. Okay. So, you can do summation of Xij for all j and given I is equal to 1 or 2. Okay. So, then you will have the value of x1 bar. So, similarly you have x2 bar, x3 bar, and you can also calculate x bar, which is essentially summation Xij for all. So, let us say this is j equal to 1 to n1, where n1 is the total number of is the sample size of population 1. Okay. Similarly, you can do all. So, Xij by n, where n is defined as summation of ni. Okay. So, you can define this x bar, and what you do, so your sample sizes are n1, n2, nk, where k is the total number of populations. Okay. So, you calculate few metrics, let me write it in the next page. So, you calculate something called TSS, or total sum of squares, and you define this as Xij minus x bar whole square. Okay. So, x bar is the average of the all the samples together. Okay. So, you can expand this and write this as Xij square minus summation Xij whole square by n. Okay. So, summation Xij is equal to G. Okay. So, G denotes the grand total of all observations. Okay. And this term, okay, so this term is referred to as correction for the mean of the mean or for the mean, and referred to as Cm. So, your Cm is given by summation of Xij whole square by n. This pen is not good. Okay. Now, this total sum of squares is divided into two components. So, you write TSS is equal to one component called sum of squares for treatments and sum of squares for errors. So, E is for error and T is for treatment. Okay. So, you can compute, okay, you can compute SST as and this can be expanded to be written as Ti square by Ni minus Cm, okay, where Ti, okay, corresponds to total of sample I. Okay. And you have the sum of squares of errors, and this is given by the sum So, the degrees of freedom or df corresponding to, okay, so you can write for TSS, SST and SSE, you can write the degrees of freedom. So, for TSS, okay, so TSS is this, and it has a total of n terms, okay, contributions of n squared terms. Okay. So, degree of freedom of TSS is n minus of 1. SST accordingly you can see has k terms. So, degree of SST is k minus 1, and degree of SSE is going to be n minus k, okay, and that you can make out from this term. You have n1 minus 1 plus n2 minus 1 dot dot nk minus 1. Okay. So, n1 minus 1 plus n2 minus 1 dot dot nk minus 1, you have summation ni, let us say, and minus 1 into k. Okay. So, since summation ni is n, so this comes to be n minus k. So, what you do, you can see that n minus 1 minus k minus 1 equal to n minus k. So, you can write down the expression, that df of TSS is equal to df of SST plus df of SSE, okay, and you can formulate the ANOVA table. Okay, you can formulate the ANOVA table, and this is given by, so you have source, you have the degrees of freedom, the total sum of squares, the mean square, okay, and you can compute the, based on this you can value the f value. Okay. So, what are your source? Your source includes treatments, error, and in sum this is total. Okay. So, this is k minus 1, this is n minus k, this is n minus 1. Okay. So, you can calculate this as, so you just write SST or SSE, and this is your TSS. This is given by SST. So, this is the mean square, either the mean square of treatments or mean square of error, and this is given by SST by the corresponding degree of freedom. Okay. Okay. So, this gives you the mean square value. So, let us revisit the problem we had solved yesterday, okay, where we had tried to correlate, if we asked the question, if nutrition has any influence on attention span. Okay. And what we had was, you had three conditions: no breakfast, okay, light breakfast, or heavy breakfast. Okay. So, you can accordingly calculate. So, you can find out. So, in this case our treatment, okay, for this problem our treatment is nothing but having the meal, or you can write it as meal. Okay. So, I will just jot down the final values that we had obtained. Okay. Meal is your treatment, error and total. Okay. So, for this case, let us say if you wanted to test the hypothesis, okay, if you wanted to test the hypothesis whether nutrition has any influence on attention span, how will we find that out? We will test the hypothesis. Okay. we will test the hypothesis mu 1 equal to mu 2 equal to mu 3. You have 3 conditions, and for you assume that there is no difference on of nutrition on attention span. Okay. And so, if for doing this you need to calculate. So, you have to calculate some test, okay, compute some test, and what you do. So, the inherent assumption of sigma square, that this is the variance is same for all k populations. Okay. So, our MSE, which is given by SSE by n minus k, this provides us with a pooled estimate of sigma square. So, if H naught is true, then MST also gives us an estimate. So, MST also provides us with an unbiased estimate of sigma square. So, you can calculate the test statistic as F. You can use the F test, where you define F by MST by MSE. Okay. So, depending on your significance level, if this value is very large, then you can rule out H naught. Okay. So, in our case, let us say for this example that we did, okay, we can calculate the F value, okay, is 29.27 by 5.93, and it comes out to be 4.93. Okay. So, for this case F turns out to be 4.93. Okay. So, you can to ask, okay, so you can calculate from the F curve, you can ask, okay, what is F 0.05. Okay. So, then in that case alpha is equal to 0.05, and what you see is F of 0.05, if you look up the tables, it comes out to be 3.89. So, this implies, since our F value of 4.93 is much greater than F of 0.05, this implies I can reject H naught. Okay. I can reject H naught, and if I reject H naught, okay, if I reject H naught, then the next question comes is, can I come up with a confidence interval for means or the difference of means. Okay. So, the question becomes, can I estimate the difference in means or in treatments. Okay. So, for this you can use the student's t test, okay, where your confidence interval, okay, your confidence interval is given by x I bar plus minus t of alpha by 2 s by root of n. Okay. And for difference of two means, it becomes, okay, okay. So, for the case, for the previous case, okay, for let us say for no breakfast, okay, for no breakfast, you know the value of S square came out to be 5.93, okay, and its DF was n minus k equal to 12. So, the confidence interval becomes x1 bar plus t of, and for this your x1 bar was 9.4. Okay. So, you can calculate the confidence interval as, okay. So, this comes out to be 9.4, okay, plus minus 2.179 into 2.436 by root of 5. Okay. So, this is square root of 5.93. This is a square. So, you can compute the value of s as root of this value, okay, and n1 was equal to 5. So, this is correspondence interval corresponding to alpha equal to, so corresponding to 95% confidence interval. Okay. So, this would come out to be 9.4 plus minus 2.37. Okay. You can similarly estimate the difference of means between light breakfast and heavy breakfast, and that comes out to be 1 plus minus 3.36. Okay. So, if I were to plot, okay, if I were to plot the three conditions and the distributions, okay, this is what the curve would look like. Okay. So, this was no breakfast, light breakfast, heavy breakfast. So, what you can clearly see, if you see the trend, if you see the trend of this, okay, it gives us the feeling that this is like a saturation curve. Okay. So, there is a statistically significant difference between these 2 points or between these 2 points. These 2 points may or may not be different, but between these 2 points there is very little difference. So, we can also use ANOVA, okay, we can also use ANOVA for linear regression, okay, which we had done long back. Okay. What is linear regression? Imagine you have two variables x and y, okay, and you plotted the points together. Okay. Let us, this is the data, raw data of x and y, and the question you wish to ask is, are x and y linearly related? Okay. So, if they were really linearly related in a deterministic sense, okay, if there was in general, okay, if you had all these points fall on a line which is exactly following a straight line equation, the equation of this line would have been something like alpha plus beta x, okay, where this intercept is alpha and the slope is beta. So, beta is slope. Okay. But as you can clearly see from these data points, there is a scatter. Okay. So, they obviously do not fall on the given line. Okay. So, to get an idea of this, what is often done is to say that on top of this line, imagine at all individual points I add a noise term. Okay. Okay. So, what I have drawn here, okay, so this is as if your equation of the line was y equal to alpha plus beta x plus some error, okay, and E epsilon is a random error, okay, with mean of 0, okay. So, random error and follows a normal distribution. So, follows normal distribution, okay, it follows, or epsilon say follows random normal distribution with mean of 0 and variance of sigma square. Okay. So, it is possible, okay, so it is possible, okay. So, on top of this line you can add a random error at every point. Okay. Let us say you add a random error, okay, to generate these random points, okay, these points around the mean, around this line, and hence by you generate some randomness. Okay. So, these points no longer fall exactly on this line, but there is some scatter. Okay. And how do you find out? So, that also brings us to question that what should be the final values of alpha and beta. Okay. And as you have done earlier, you know that we use the least squares approach. Okay. So, what least squares approach does, it may essentially minimizes these errors. Okay. It minimizes these errors on both sides of this line. Okay. It minimizes these errors, or rather the square of these errors, thereby finding some estimate of alpha and beta, and this least square line is written as y is equal to a plus bx. Okay. So, in next class we will discuss how ANOVA can be used to test the possibility that this linear regression makes sense or not. Okay. Thank you for your attention.